In example 57, we think about the situation where we're going to roll a pair of dice and record the sum. And so the outcome of this particular experiment is we just write down what our dice add up to. And somebody, maybe perhaps suggests that we could use this as our sample space. These are the possible outcomes, right? I mean, I can't get anything less than 2 because that's double ones, and of course the highest thing is 12 for double sixes. And we want to know, why is this not a good sample space to use? Well, it all comes from the fact that when we compute a theoretical probability, we're always dividing by n of s, the size of our sample space, the number of possible outcomes where these are all equally likely. So the reason that this sample space isn't a good one to use, first of all, in this situation, the size of our sample space would be, 11, I guess, right? 2 through 12. The reason we don't want to use this is because these outcomes are not equally likely. For example, if I wanted to, if I considered how many ways could I get a 12? There's only one way to get a 12 once you roll a pair of dice. Right? It has to be double sixes, which I'll express as an ordered pair here. However, let's think about now, how many ways are there to get a 7? Well, I could roll a 1 and a 6. I could roll a 2 and a 5. Or I could roll a 3 and a 4. Right, so just looking at this example here, I could see that writing out my sample space like this, as they have in this example, those aren't equally likely outcomes, and so it's not a useful sample space to use from a probability perspective. It won't be, I don't want to use 11 as my denominator when I compute probabilities in the situation where I roll a pair of dice. So here I've listed the ways we can get a 7. In fact, as we'll notice on the next page, we're going to actually have to double this, because I could get a 1 and a 6, or I could also get a 6 and a 1. And you might be wondering, well, that's really the same roll, isn't it? I would say it's the same roll as far as how we interpret the outcome, but we need to count them separately. And so on the next page, we've got basically, here's the sample space we want to use when we roll a pair of dice. I want to consider each possible permutation of events, whether I get a 1 on my first die and then a 6, versus if I get a 1 on my second die and then a 6 on my first die. I'm going to count those separately, even though we interpret them as being basically the same outcome for the purposes of, whatever game we might play. We want to count them separately, and here's the reason. When I think about rolling a white die and a black die versus just a pair of dice, we could see that there's 2 ways I can get a 1 and a 6. Right? I could have a 1 on the white die and a 6 on the black die, or a 6 on the white die and a 1 on a black die. However, when I think about rolling perhaps double 3s, there is only one way to get double 3s. They both have to come out to 3. You'll see no other instance in this listing here where you have both dice coming out as 3. And so we need to include both orderings of distinct rolls here in order to have a meaningful sample space. So 6 possible outcomes from one die, 6 possible outcomes from the other die. Multiplication counting rule tells us, and you can count them up here, there are 36 possible outcomes that we need to consider. And so our sample space for rolling a pair of dice here, the size of our sample space will be 36.